Good morning, students. Let us start the lab class. I was waiting and hoping that some more students will join, but only 5 are there now. Me and Deepak should consider that it is our fortune that at least 5 have joined. Okay. Yesterday, in somebody's WhatsApp status, I saw one comic strip and it was telling offline class, teacher keeps telling to the students, don't talk, keep quiet, don't talk, keep quiet. In the online class, teacher is requesting the students, please talk something, please respond. Anyway, the funny part, boy, away. Let us start the class for today. So today we are going to discuss the very last experiment in the analog cycle. Later on, we will be discussing the digital cycle only. And in the digital cycle, only in the beginning, there are a lot of procedures to be discussed. Later on, as far as experiments are concerned, we need not discuss a lot. Whereas in the analog experiments, as it was made of different circuitry and design, we had to discuss a theory. So today is the last experiment called operational amplifier. There is a brief theory. Let me go through it just for an introduction. An operational amplifier of an op-amp or op-amp is a DC coupled high gain electronic voltage amplifier with a differential input and usually a single-ended output. In this configuration, an op-amp produces an output potential relative to circuit ground that is typically hundreds of thousands of times larger than the potential difference between its input terminals. As you already know, op-amp has got ideally infinite voltage gain, infinite current gain. Practically, it will have very high voltage gain. Operational amplifiers had their origins in analog computers where they were used to perform mathematical operations in many linear, non-linear and frequency-dependent circuits. Before the invention of digital computers, whether it was a von Neumann architecture or whether it was Charles Babbage's ideas, whatever it was, before that, people were using op-amps only for analog computation, for summation and multiplication and such things. And even using vacuum tubes, they used to construct such computative elements. You must be knowing about ENA-IDC, Electronic Numerical Integrator and Calculator. Electronic Numerical Integrator and Calculator, something like that. ENAC, something like that. That computer was as large as a big hall, and the heat that was generated by the computer was used to boil water and produce steam, and that steam was used to run one more steam engine, and the power produced by the steam engine was supplied back to the computer. That was the size of the computer in those days. And they were all analog computers, and even op-amp was used in the analog computers. Of course, now as everything is digital, no use of op-amp in case of computation now. We are using it only as an amplifier now. So the popularity of the op-amp as a building block in analog circuits is due to its versatility. It can be used in open loop as a comparator, in closed loop with so many other mathematical applications. Or otherwise also, as I had told in the previous class, if we have a differential input and differential output amplifier, then it will have a very large CMRR, due to which the noise effects can be minimized. By using negative feedback, the characteristics of an op-amp circuit, its gain, input and output impedance, bandwidth, etc. can be increased. So let me proceed with the circuit directly now. You can see the circuit of op-amp now. You can see the portion. Let me write a border line in between. Okay. Crudely, I wrote one block there. Now you can see the left side, whatever you are seeing is the regular differential amplifier. And as we discussed in the last class, V1 is the non-inverting input and V2 is the inverting input. This we had discussed in the last class. And the lower transistor here, it is the current source where we give the DC current supply there. Then the right side transistor NMOS below, that is the current mirroring transistor, and above which we have two PMOS FETs which are used as resistors in the linear region. Again, by shorting gate with the drain, we are making VDS is equal to VGS and we are forcing the transistor to work only in the saturation region, preventing it to come to the linear region. And as the gates are connected, there is also current mirroring concept there. So the left side, whatever you are seeing is the regular differential amplifier which we had discussed in the last class. Now can anybody tell me what is this amplifier at the right side? It has actually two amplifiers. It's a two-stage operational amplifier where there are two now. At the input you have a differential amplifier, at the output there is one more amplifier. Okay, Kuldeep is saying it is a common source amplifier. Okay, Kuldeep has understood, but let me ask him further questions then. In the earlier case, when we used common source amplifier, we had used one PMOS and NMOS, where NMOS we used as the amplifying transistor and the PMOS we used as the resistor. Now here you can see the gate of three NMOS FETs are connected together, which means there is this current source and then we have a current mirror. The same current mirror is applicable to this NM4 also, the NMOS at the bottom. So obviously the lower transistor is not the amplifying transistor. The upper PMOS is the amplifying transistor, right? So my question is, can you elaborate now? Can we use a PMOS transistor here as common source? Okay, he's putting yes, sir. He has put a comma there, so I think he will type some more elaborate answer. Fine. You can see here this PMOS FET, to the gate we are connecting input and at the drain we are taking output. As the source is connected to power supply, source is AC ground. So here instead of NMOS, PMOS FET is used as the amplifying transistor, and below we are connecting the NMOS FET as a resistor. This NMOS FET used in the linear region. You can see the width of this NMOS FET is 20 micrometer when compared to this particular NM2 where it is only 4.5 micrometer. So by means of the device dimension, NM4 is kept in the linear region, so it is working like a resistor there. So across the resistor we are taking the output. So this is also a common source amplifier only. The only difference is it is PMOS FET which is the amplifying transistor. Now let me write further. So we have this two-stage op-amp now, where you have two inputs, then we have one more common source amplifier. Okay. So we have this minus and plus two terminals here for the differential amplifier. Then the differential amplifier's output is connected to a high gain stage. This common source amplifier itself is this high gain stage. So this is basically a two-stage amplifier. As I've been telling you earlier, in your next semester, you can take the op-amp design itself as a mini project for those of you who are interested in the VLSI designs. You can try to design your own operational amplifier, maybe 2-stage, maybe 3-stage also. You can have an intermediate stage in between, then you can have a high gain stage. At the output, you can have a power amplifier also. You can refer to the published articles or even to the textbooks, and you can design your own operational amplifier, and you can measure its gain and bandwidth, and you can proceed with the physical design also or with the layout design also. That will be quite interesting. When you come to final year, you can use the same op-amp for some other bigger designs. Using the operational amplifier, you can design some other bigger circuit block as such. So you can extend this idea even for your final year project. You will be thorough with the circuit design and along with the other mathematical designs also. So you can see here differential amplifier and the high gain stage. Now the one more small problem or issue or whatever. You can see one capacitor here. Any guess why this capacitor may be used? Because it is connected as a feedback between output and input. Now you know that in a common source amplifier, let us say we give input here. Let me change the color. Let us say we are using non-inverting input itself, and let us say the output here is also in the same phase. Now this common source amplifier is going to give a 180-degree phase shift. We are giving input at the gate, and in the negative cycle Pmos is going to conduct, and when Pmos is conducting, there is a voltage drop across this resistance, and in the negative cycle we will have the corresponding positive cycle. In the positive cycle, slightly Pmos is going to move towards the cutoff region, and the voltage across this resistor will reduce, and that is when we have this negative cycle. So common source amplifier is going to go a 180-degree phase shift. We already know about it. Now between output and input, as there is a phase shift, output is connected directly back to input by means of this capacitor. There is a feedback now, and the feedback is a negative feedback. We wanted an operational amplifier which is supposed to have very high gain. Now when we are giving this negative feedback, naturally the gain is going to be reduced. What may be the purpose of this capacitor? Any guess? Okay, Kuldeep is honestly telling, don't know. Fine. What about other students? Any guess? Alright, let me tell the answer when I discuss the frequency response. So I hope you have understood the circuit functionality now. This is a 2-stage operational amplifier, and with the VDD and VSS with the dual power supply. Let me proceed to discuss about the simulation. You can create a symbol like this. For an operational amplifier, you have an IDC, and we have V1 and V2, and we have an output. So this symbol can be created, and afterwards the symbol can be connected with the two resistors. You can see at the left side there is power supply VDD and VSS. We are using plus 2.5 and minus 2.5 for VDD and VSS. And we are giving a 30 microampere DC current as a biasing current. And you can see at the input we have connected a sinusoidal AC source, with the 5 millivolts, amplitude, frequency 1 kilohertz. As op-amp is having a very high gain, we have connected a feedback resistor. As V1 is minus, you already know that V1 is minus, V2 is plus. So we are connecting a negative feedback here from output back to input, 500K by 1K. So AV is going to be minus of RF by RI. RF is 500, RI is 1K. So we have configured the gain to be around 500 times in the inverting mode. That is how we have chosen these two resistors. You are already familiar with the op-amp circuits as such. Now you can see here there is polyres. Polyres R equals 500K. In the GPDK 180 library, you can choose this polysilicon resistor. Means, as I had mentioned you earlier, when we need a resistor, we will have to use those layers, either polysilicon or NWell, which have enough resistance there. So as polysilicon layer is having resistivity, we can use it itself as a resistor here, because finally we have to make a layout inside the chip. It is not like the resistor which is discrete. Now this is an integrated resistor. The resistor will be of a much larger area when compared to the transistor itself now. If at all you have to have a 500 kilo ohms resistor, a large area has to be reserved for it, as R is equal to rho into L by A. That is why this polyres is chosen. Otherwise, in the analog lib library, you already have a resistor, but it will not be converted into layout when you go for a physical design, because the analog lib components will not have a layout part there. They are defined only for simulation purposes. Just like these voltage sources, they do not have any layout there. But we purposely choose polyres because later on we can actually make a layout by taking the dimensions of this resistance in the polysilicon layer. That is the idea here. So 500 kilo ohms is the feedback resistance, 1 kilo ohms is the input resistance. So the gain which we are setting now for this amplifier is around 500 times. Let me proceed. You can see the simulations output now. At the left side you are seeing the input waveform and the output waveform are actually anti-phase. You can see that there is a 180-degree phase shift. And you can see the upper waveform is input waveform where it is in millivolts, 5 volts to minus 5 volts. Totally it is 10 millivolts peak to peak input signal. Whereas at the lower side you can see it is in volts, not in millivolts. Output is in volts. It has gone up to minus 2.5 here and it has gone up to plus 1.5 or about 1.7 here. So the output is in volts, there is almost 500 times gain. You can see here in the middle curve, you can see input is in few millivolts, output is very much nearer to 500. It is slightly less than 500. Now that is because we have constructed only a 2-stage op-amp. If at all you make it as a 3-stage op-amp, you will get definitely 500. Now why we got here slightly less than 500, the reason is the open loop gain, we ideally take it as more than 10,000 or so, right? But here in this lab experiment, we have constructed only a 2-stage op-amp. We have not put the middle stage, or we have not put the intermediate stage for a higher gain also. That way, this particular circuit's open loop gain will not be reaching to 10,000. In that case, all the ideal equations of the inverting amplifier are not applicable. That is when, even though we have connected 500K and 1K as two resistors, we are getting a gain slightly lesser. That is why I had told you, in your mini project, you can take up a design of a 3-stage op-amp where you can achieve a much larger open loop gain. Actually, you can measure the open loop gain also for the amplifier without connecting the resistors as such, just like the way in which we did in the differential amplifier. So you can see the gain nearly 500, but what about the bandwidth here? You can see the bandwidth here. Bandwidth is not even 1 megahertz. You can measure this. From the gain, come to around 0.707 and come down, you can see that the bandwidth is less than 10 power 6. That means the bandwidth is less than 1 megahertz. So GBP, if at all I calculate GBP for this operation amplifier, let us say. Let me write GBP. GBP. If I take gain as 500 approximately, and you can see the bandwidth here. Bandwidth is somewhere around 200 kilohertz. Approximately I can take it as, because 10 power 5 is 100 kilohertz, somewhere around 200 kilohertz. So I can write it as 0.2 megahertz. So 500 into 0.2 is only 100. 100 mega is the gain bandwidth product of this particular op-amp, which is actually much lesser. We are discussing about gigahertz nowadays. We have applications which are working with gigahertz. And this particular operational amplifier is having a very less gain bandwidth product. Now that is the challenge here. Why bandwidth became so lesser? Any guess? In our differential amplifier, we had a slightly larger bandwidth. Why bandwidth became so less here? Any guess? There is feedback. Okay. Feedback. No. With the negative feedback, actually gain will reduce, bandwidth will increase, right? The feedback which we are giving through that capacitor is basically a negative feedback. So when we give a negative feedback, advantage of negative feedback is the gain will reduce and bandwidth will increase. It is not because of that feedback. The reason is at the output, you have common source amplifier which is having a added parasitic capacitance. Let me show you the circuit diagram. You can see here the common source amplifier P MOSFET is 50 microns and the N MOSFET is 20 microns. You know that C is equal to epsilon into A by D, right? A is what? W into L, right? Let me write. C is equal to epsilon A by D, where D is the thickness here. We can write it as T also in this case. Now what is A? W into L by D. So when W increases here, naturally capacitance increases. So larger the capacitance of the device, we have a problem with the high frequency cutoff. You have already studied in the third semester that high frequency response is mainly dependent on the internal parasitic capacitances. Larger the internal parasitic capacitances, lesser will be the bandwidth. That is the reason. And to some extent this feedback is there, but as I told you, negative feedback is also always going to increase the bandwidth because it is reducing the gain, right? Now because of that negative feedback only, there was a reduction in gain. Instead of 500, we are getting slightly lesser here. That is because of the negative feedback. Now the reduction in bandwidth is not because of that capacitance. It is because of the internal capacitors of the transistor where the device dimensions are larger. Now that is the problem with operational amplifier now. You want to have higher gain also, you want to have higher bandwidth also in both cases. But when it comes to practicality, ideally we have to find the operational amplifier. When it comes to practicality, we can see that we don't get both. And now it is a challenge how to get a larger gain bandwidth product for a given operational amplifier. That is why I told you that design becomes critical. When you design on your own, let us say a 3-stage amplifier with a larger gain bandwidth product, you can actually patent it. If you become successful in designing a different op-amp or a better op-amp which can have a larger gain bandwidth product which the industry requires. You can patent it, that becomes your product there. That is the challenge there. That is why I told you can extend it to the final year project also. But it requires a serious study, serious calculations part, serious understanding of the basics. Fine. That is about AC response. At the left side, you are seeing transient response. In the middle, you are seeing AC response. At the right side, you are seeing a DC response or a transfer characteristics. So from minus 2.5 till plus 2.5, when we move our input, here you can see the output has remained up to plus 2.5 to some extent. Then suddenly there is a steep downfall and it is coming down to minus 2.5. What does it mean? This means that when input was minus 2.5, output was plus 2.5. We had used it in the inverting mode, right? So in the DC response, the feedback is not considered. It is the transfer curve that is considered directly. The feedback resistors are not considered when the cadence tool plots the DC response as such. So you can see the amplifier is in the positive saturation when the input is totally negative. That means the open loop gain is larger. And suddenly at the quiescent point, let us say at 0 point, between minus 2.5 plus 2.5, there is a steep downfall. And then when the input increases further, output saturates to the negative side. When the input crosses 0, when the input is becoming positive, output is becoming completely negative. This is what is expected out of an operational amplifier, right? When you use the operational amplifier in the open loop, then it is going to work like a comparator with respect to ground. Now you can see when the input is minus 2.5, other one is connected to 0. So it is working like an inverting comparator there. Now, as soon as the input crosses above 0, input is becoming positive, it is going to the negative side. So that means you will have to recall whatever you studied in the linear integrated circuits course. This is now plus Vsat, this is now minus Vsat. It is almost 2.5 here. You can see almost 2.5, very much nearer to plus 2.5. Here also it is almost nearer to minus 2.5. Of course, there will be some slight drops across the transistors there, a few millivolts. Otherwise, it is almost plus Vsat and minus Vsat is plus Vcc and minus Vcc. So that way this op-amp is a good design as far as a comparator activity or comparator functionality is concerned. Now where are we using it as an amplifier then? We are using it as an amplifier in the closed loop condition by connecting the feedback resistors. And actually we are using it here. We are using it as a small signal amplifier only by fixing the quiescent point at 0. So between minus 2.0 plus 2.0, you can see there is a small gap here and there is a small gap here. We can use this like a amplifier in the open loop gain exactly here, because there is a steep change later on, because it is working like a comparator. But otherwise, when we connect a negative feedback, it is anyhow not going to saturate to the plus Vsat and minus Vsat, and we can use it as a regular inverting amplifier only when we connect a feedback. So that is the advantage of using MOSFETs when compared to BJTs, that the biasing arrangement is simpler in case of MOSFETs when compared to BJTs. BJTs require a complicated voltage divider bias network at the input to set the Q point. Whereas in the case of MOSFET, such complications are not there. Moreover, when we use dual power supply, the effort for fixing the Q point is minimum there. So now I have discussed the transient response, AC response and DC response. Now let me come to that point why that capacitor is used. Before that, let me discuss the gain curve and the phase curve. Upper one is the phase response, lower one is the gain response. The gain is almost 500 there. Corresponding to 500, you can see the gain in decibels here. It is somewhere around 53 dB or 54 dB. So this is the gain. Now when you come down, you can see we have to come down to around 3 dB down. So you can see somewhere here. It is only around 200 kilohertz. You can see here, no? This is 10 power 5, 100 kilohertz, 200, 300, 400, 500, 600, 700, 800, 900. Yeah. So 200, around 400 kilohertz. Around 400 kilohertz or 0.4 megahertz is the bandwidth here, corresponding to around 53 dB gain. So here we can accurately write the GBP using decibels as 53 dB, approximately it is 53 dB into 0.4 mega. In terms of decibels we can write. So 4 3 12 1 5 4 21 21 point. So approximately 21 dB mega. This is the gain bandwidth product, which is actually quite lesser. Now, when the bandwidth is somewhere here, the gain is going down here. Gain has not yet reached 0. And you can see the phase responses are coming down from 180 degree. It is coming down just after about 10 kilohertz, around 20 kilohertz, 30, 40, 50. It is coming down here. So the phase is also coming down. Now we have this gain margin and phase margin problems where these two should not be meeting the line at the same point, right? Whenever the gain is becoming 0 dB, the phase should not become 0 at that time. So see, minus 180 and the phase has become 0 here. Now you can see the phase margin here. Phase has become 0, but gain has not yet become 0. When the gain becomes 0, there you can see the gain margin also. So there is this phase margin and gain margin. Larger the phase margin, larger the gain margin, more stable is the circuit. This is with respect to gain curve and phase curve. Now, you can connect it as a non-inverting amplifier now by connecting the feedback resistance to the positive terminal and connecting the input to the positive terminal. Sorry, not connecting the feedback to the positive terminal. The circuit will remain the same. Only thing is the series resistors other end is connected to ground and input is applied to the positive terminal, inverting, non-inverting terminal. So you can see here there is no phase shift at the output because we are now configuring the op-amp in the non-inverting mode. The gain formula will slightly change to 1 plus RF by RI, but 500 becomes 501 now, that's all. That is a minor difference there which can be ignored. So now you can see because of that negative feedback of the capacitor, gain is slightly reduced and the bandwidth also has remained the same because it's the same circuit. There will not be any change as far as the gain and bandwidth are concerned. But in the DC response you can see when the input is rising until 0, input has remained at minus 2.5. Suddenly near 0, output has gone up. Actually, output has remained at minus 2.5. Output has gone up suddenly to plus 2.5. And afterwards, it has remained at plus 2.5. I had told you about the Q point there. Now, this is the Q point where we can use it like a small signal amplifier in the open loop gain also. So otherwise the gain is really very high. You can see it is saturating from minus Vsat to plus Vsat. Now you can see it is in the non-inverting mode where and the input is rising, output is also rising. So that way, the transfer curve indicates its phase shift. In this case, there is no phase shift at all. So this is the working of the operational amplifier in the non-inverting mode. That's all with this now. Now let me come to the gain curve. Let me discuss. Yeah, you can see the phase and gain curve here. Here the phase curve is starting with 0 degree. There is no phase shift because of the non-inverting amplifier. Gain remains the same, bandwidth also remains the same. And you can see when the phase becomes 180, it has not yet become 180. From 0, phase has to become 180. Gain has to become 0. Here in this curve, it is not actually visible that way. When you actually conduct this experiment, you can increase this frequency from 10 power 7 to 10 power 9 or 10 power 12. You can actually measure the gain margin and phase margin. So after the simulation, here we have not shown the layout because for the differential amplifier, only one additional common source amplifier is there. We have already shown you the common source amplifier's layout. We have already shown you the differential amplifier's layout. You will have to connect them together and complete the layout and perform the physical verification using Ashura. And here you will see more parasitics compared to the previous experiments. This experiment will have the largest amount of parasitic capacitances because this has got totally now 8 transistors, right? Totally 8 MOSFETs, and common source amplifier is having a much larger dimension. So, if at all those students who are interested to perform back annotation, we will tell you here when we start the offline lab about how back annotation can be done. Of course, I don't know how much time will be there for you to perform all those things now. Still, even in the next semester also, if you take up this as a mini project, you can actually perform a back annotation where you can see the difference between the values obtained just by simulation and obtained after physical verification. There will be a drastic difference there. Whatever gain and bandwidth you got just by simulation, if at all you perform the same thing after physical verification, definitely there will be a degradation in the gain and the bandwidth response because of the parasitic capacitances. Because during simulation, we did not worry about the parasitic capacitances. All of them come into picture when we complete the layout. That is the idea. Now let me tell about that capacitor. To conclude, before that, let me tell about the capacitor. X-axis is frequency and y-axis is gain in dB. Now, as this is a direct coupled amplifier, we can say that the gain curve is like this. We can say this way. This is in general, the gain at the higher frequencies reduces because of the parasitic capacitances. Now this is what we have obtained in this experiment. But if at all you remove that capacitor, then you will find the gain response something like this. Now can somebody tell me, I have written a red line where the gain response is not actually ideal. Gain is going down at the higher frequencies, but somewhere there is one overshoot. Can somebody tell me why this overshoot is occurring? We have this overshoot. Actually, when you conduct this experiment, you can remove that capacitor, you can perform your simulation, you will get a response like this. Can somebody tell me why we get this overshoot? Any idea? No idea. Now Kuldeep is also not responding. Okay, because it is online class. Fine. Okay. If it is offline class, I would have forced you people to speak something at least. The overshoot is basically the non-ideality. Non-ideality of the devices now. As the devices have their own parasitics, all the devices become frequency selective. In the sense, in the high frequency ranges, the devices will not obey any of those laws which we actually frame about it. Even the models which we have in the cadence library may not be completely accurate even in high frequencies. That's the problem there. I have told you about the work done, I think I have told you, in Berkeley University in USA, people have done very elaborate, much bigger work on modeling of the MOSFET itself for different technologies, where each MOSFET is modeled with more than 200 equations, multiple level differential equations. That is because at high frequencies, we should have more accurate models. Now this transistor, now you may ask me, sir, here during simulation only we got this. No, yeah, because we have an accurate model in cadence when compared to PSpice. PSpice will not be having this much accurate model. Cadence is supposed to have much accurate model because we are going to get these things manufactured. So when we use these models, those models will have the device parasitics also defined and their high frequency behavior also defined. So at some high frequencies, somewhere the gain provided by the op-amp may have sudden undershoot or overshoot. That is because of the impedance there. Now we'll have to model all these 6 plus 2, 8 transistors together, and the impedance will not be ideal, or impedance cannot be so easily calculated that way for each frequency. Now the simulator tool has got the MOS model, and at this particular frequency range, suddenly there is an increase in gain. This is one case I am showing you. There can be a decrease in gain also somewhere. There can be an uneven curve also somewhere. The curve may not be flat at all, even in the mid band. Now that is not what we expect. We expect at least in the mid band the curve should be flat. Now how to make the curve flat in the mid band? The only way is to reduce the gain by applying negative feedback. That is what we have done. We have purposefully connected a capacitor and we have given a negative feedback, and then we reduce the gain slightly lesser. It is not 500, it is less than 500 because of that only. When the gain is reduced, we get a flat response here. That is the advantage of negative feedback. Now my last question is, what is that capacitor called? That capacitor has got a specific name. Anybody can recall the name of that capacitor? Even though it is a feedback capacitor and even though it is connected with an output back to input to provide a negative feedback, that capacitor has got a specific name. Right. My very good student Kuldeep is responding again that it is a Miller capacitance. I congratulate Kuldeep. At least you have been highly active in all my classes, theory classes also, lab classes also. When you come back to college, you should meet me. Okay. I personally want to congratulate you. So Kuldeep has told Miller capacitance, right? That way, some scientists like Fourier, mathematicians like Fourier and Laplace, and scientists like Nyquist and Miller, they have done a lot of work with the electronic circuitry. Fourier and Laplace have given a much better insight into time and frequency domains, whereas Nyquist and Miller studied a lot about the stability of the circuits, electronic circuits especially, and how to attain stability by compromising other things. We can compromise on gain, we can compromise on bandwidth. Main thing is stability of the system or the circuit. So that is where Miller had modeled a transistor, because if you remember the BJT is common emitter amplifier, emitter is common to base and collector, and between base and collector normally we ignore the capacitance, that junction capacitance or the collector to base parasitic capacitance. Normally at the low frequencies we ignore, but at the high frequencies we cannot ignore. So how to model that particular capacitor at the input as well as the output? That is when Miller did a great contribution by modeling that particular feedback capacitor in terms of input capacitance and output capacitance. Now that capacitance was by default present there between base and collector. Here what we are doing, we are connecting the external capacitor between output and input for reducing the gain, for providing negative feedback. To honor Miller, we are calling this capacitance also as Miller capacitance. Even though this capacitance is not internal, it is external. In fact, Miller modeled the capacitance which was internal, right? Now here also you have the capacitance between gate and drain. You will have that capacitance inside. That is the parasitic capacitance. Between gate and source also, we will have a parasitic capacitance. MOSFET means always capacitances inside also. But for providing negative feedback, we have connected an external capacitance. So to honor Miller, we are keeping the name of this capacitance also as Miller capacitance. Fine. My very last question now is, let me zoom and let me ask you. Now you can see this capacitance is named as MIM cap and its value is 104 femtofarad. This I had purposefully chosen at that time when I simulated the circuit almost 10 years before. I think it was in 2010 when I simulated the circuit. So I had chosen this value as 104 femtofarad so that the gain should not reduce further. Approximately we can say it is 100 femtofarad. 100 femtofarad or it is around 0.1 picofarad, right? Right, no, it is milli, micro, nano, pico, femto, atto, zepto, yocto. 10 power minus 12 is pico, 10 power minus 15 is femto, 10 power minus 18 is atto, 10 power minus 21 is zepto, 10 power minus 24 is yocto. So this is 104 into 10 power minus 15 or approximately 0.1 picofarad. If we connect a larger value of capacitance, we will have further reduction in gain. I chose this value only to reduce that overshoot which was occurring in that gain response. Otherwise, if we increase the value of the capacitance, we will have further reduction in gain. That is not desirable. Now, when I showed you the resistance, I told it as polyresistance. Polysilicon is used as resistance. Now, I want my students to guess about what is this MIM. We have MIM cap. Cap is capacitance. What is this MIM? Can anybody guess this? It is related to layout. It may be difficult for you to guess. So let me write. MIM is metal . Last M is also metal. Now can you guess the I in between? This M is metal, this M is metal. What is this I? Can anybody guess? No guesses. Okay. Insulator, right, Kuldeep? It is insulator, metal, insulator, metal. Now, for fabricating a resistor, we use a polysilicon. For how to fabricate a capacitor now? For fabricating a capacitor, we have this metal 1 and metal 2. Between metal 1 and metal 2, there is already an insulator, right? Silicon dioxide is an insulator there in between two metal layers. It is part of the process itself. So, we need two plates, conducting plates for a capacitance. In between, we need insulator. Now, inside the chip, we can use these two metal layers only as the two conducting plates for the capacitance. And we can use the insulator in between the silicon dioxide itself as the insulator for this capacitance. So, when you make a layout, that is going to be really very beautiful, where when you make a layout of this op-amp for this capacitance, the tool is going to give you a different structure. For this 104 femtofarad itself, area is defined. So, it will give you a beautiful square or rectangular structure where one end is metal 1, other one is metal 2. Now you will have to connect a metal 2 along with the wire, metal 1 along with the wire, because here the gate is now what? Gate is polysilicon. Now drain is now what? Drain is implantation, right? Drain is P implantation inside N well, and gate is polysilicon. You need a wire from metal 1 or metal 2, depending upon which side you are keeping where. From metal 2, you need one more wire to the drain, let us say. Let us say this is now M2, and let us say this is now M1. Here you will have M1 to poly as a wire, and here you need a M2 to P diffusion, P implantation as a wire. So you'll have to use all those wires when you connect this capacitance. So with this, I am coming to the end of today's class. If any of you have any questions, you can ask me. I will wait for a few minutes, or else I will stop sharing this screen. Meeting will be on for the submission of your observation book. I think Deepak has already put the attendance link. I don't know. Deepak, are you there?
Yes.
Okay. Create the assignment for today's observation book also.
And assignment also.
Okay. Okay, if students have any questions, you can unmute and ask me, or else I will stop sharing and I will stop recording also. Okay, as there are no questions, already students have started leaving the meeting, so let me stop recording, let me stop sharing.